Hello, everyone. Welcome to the course CE597 Advanced Structural Testing. My name is Yu Guangfu. I'm a postdoc at Purdue University. Today we'll talk about digital signal processing and filter design. This is outline of today's lecture. We will quickly go through the background of digital signal processing, which in other words is DSP. And then we will review some basic technologies or techniques for signal processing, like Fourier transform, discrete Fourier transform, Laplace transform, and Z transform, etc. Based on that, we will study how to design digital filters, including finite impulse response filter and infinite impulse response filter. And after that, we will discuss about several interesting applications of digital filters. And finally, I will summarize today's lecture. Hopefully you can enjoy the course today. All right, let's start with the background part. Signal processing is the art and science of modifying quiet time series data for the purpose of the analysis or enhancement. Okay, it's very popular and very important to our daily life. It could deal with some audio signals. For example, every people have a phone here, cell phone. Okay, imagine how does your voice come through one phone to the other. Okay, and there are a lot of signal processing techniques inside it. How to compress the audio signal, how to transmit using advanced protocols, right? Second application or second very important example is the medical imaging for diagnosis. Yeah, and for example, doctors will try like X-ray or magnetic resonance imaging to diagnose some like kind of to check your bone, to check your tuner, if there's something wrong in your inside your body, right? They try to transform their magnetic signal or radio signal to the image, and then to visualize the structure of the organs or other things inside your inside your body. Okay. Another interesting example is the aircraft tracking. Okay. Which has been widely used in both civil and military purpose. People use radar and GPS signal to try to track the position and the traveling path of the aircraft. Okay. Another interesting example is the video streaming. So these days, because COVID-19 and working from home, people use WebEx and Zoom for meeting, right? And how does that make sure that, your voice and your screen and your animation is and share and broadcast to the meeting participants in real time? That would be also very challenging and require advanced signal processing technique. All right, so what are the common problems for the signal processing to address? Well, let's start with a very basic problem, which is try to eliminate the noise in the signal. Okay, imagine you have data collected from accelerometer or strain gauge using the DAQ system. Okay, and you have a lot of noise in the time history data. How do we remove that? Well, we can apply signal processing technique. The other problem is kind of correct the distortion, right? Imagine you have there several photos taken by your phone, okay? But the photo is not well established. They're kind of have distortion in the corner, especially in the corner of the figure. Well, we can apply signal processing to like correct them. The other important problem, which is also widely considered in the area, is that to extract information or important information from the signals. Okay. Here I show a very interesting example. The researchers, they try to kind of figure out the geometry of the room using the voice signal or audio signal. Okay, they try to identify the relationship between the arrival time of the echoes and the inside geometry of the room. Okay, this is quite interesting. All right, so let's dig deeper. Okay, think about how does the signal coming through and the process using the DSP. Okay, so imagine you have the microphone. You try to record your voice and process your voice signal, audio signal, and then in a kind of broadcast or transmit to other people. Okay. So, well, the real world phenomenon is always kind of analog. Okay. We can kind of describe them as the energy level. Okay. The transducer, which is microphone here, is trying to measure the level of energy using voltage signal or current signal, but it's in analog. Okay. And it goes through ADC, which is analog digital converter, eventually becomes a digitized signal, which is easier for the chip, DSP chip or computer to process. Either applying some advanced technique like equalizers or compression or something else to try to make the voice more high quality. Okay, and then it can either store in the memory block, or goes back to analog signal by going through digital to analog converter, which is DAC here, and then broadcast using kind of loudspeaker or other devices to let other people hear about that. Okay. So here I would like to emphasize that in the center part of this process, which is DSP chip, is very important and is mainly built upon a bank or series of filters. Okay. Here you can see this is actually the figure I copied from the MathWork web page. This is actually illustrates the equalizers to adjust the voice audio signal. Okay, and basically they actually can be represented as a series of filters. Okay, they try to adjust the loudness, which is also actually the energy level in different frequency domain. Okay, from 20 to 20,000 hertz. Okay. In the demo session, we can play with that and hear the effect of the filter. All right. Now let's start with the review session. Hopefully you already get the big picture about the digital signal processing. Okay. But to better understand that, we need to kind of review some basic mathematical knowledge of, beneath the signal processing. Let's start with the Fourier series. Barry Fourier proposed that every signal, every real-world phenomenon can be kind of a waveform can be represented as the summation, the sum of the series of cosine function and sine function. So here, imagine we have xt, which is time history data, is equal to a0 plus summation of cosine and sine, okay, with different coefficients, an and bn here, okay, which is amazing. But it's actually not quite, it's easier to understand if we dig in detail about derivation, but it's not easy to kind of do the analysis and the calculation. Okay. Therefore, researcher or people, engineers think about, can we apply the Euler's formula, try to get a more compact form here, which is actually the equation here with tens, okay, is xt is equal to the summation of Cn times e to the j n omega 0 t. Okay. So the key part is the Euler formula, which represents that the vector of e to the j omega, or actually e to the I omega, is equal to cosine. E to the I phi is actually equal to cosine phi plus I times sine phi. Okay. And okay, this is also called synthesis equation for the Fourier series. Okay. And we can also obtain Cn, which is coefficient here, is actually equal to 1 over t times the integral of xt times e to the minus jn omega 0 t integral over dt. Okay, this is also called analysis formula for the Fourier series. Okay, I will not go detail about the derivation, but I share the link here. If you have, if you are interested about that, feel free to contact me or go through the link. Try to understand that. Okay. So this is the figure I got from the Wikipedia, which is, I believe, is very illustrative and helpful. Okay. Imagine you have the square signal. Okay. You want to represent it as a series of cosine sine function using Fourier series. Okay. Here it shows that how it works. And you can see that by applying a series of sine cosine function, it actually represents a square signal here. And the more items you added, the shape of the summation of the signal is more closer to the square signal. And the spike, the Stern plot here is actually the frequency domain values corresponding to the square signal. Okay. So the next part is the review of the Fourier transform. Okay. If you remember in the previous figure, you see that the result of the Fourier series in frequency domain is actually discrete. Okay. This is because it is a base assumption that the signals are periodic about a basic fundamental frequency, which is omega 0, is equal to 2 pi divided by t. If we try to extend the t to be infinity, then omega 0 is get closer to 0. In that case, we can have continuous frequency representation. This is what we call Fourier transform. So here we get a pair of the formula again, including analysis formula and synthesis formula. Okay. As you can see here is actually the integral of minus infinity to infinity. Okay. And the synthesis formula is also called inverse Fourier transform. For detailed derivation, please click the link or ask me offline. Okay. Here, I also showed a pair of some common figures about the Fourier transform. If we have spike in the time domain, then if you apply the Fourier transform, you will get kind of a uniform distribution over the frequency domain. Okay. If you have the impulse signal or delta function in the time domain, then after Fourier transform, you will get a sinc function here. Okay. Another similar transform is a Laplace transform. So it actually project the signal to S plane. S is actually equal to sigma plus j omega. Here, if you look in detail here, if we put sigma is equal to 0, then the S variable is become the Fourier transform variable here, omega here. Okay. So if you look at compare this formula together, xs is actually equal to integral of xt times e to the minus st integral about dt is actually equivalent to the Fourier transform that's replace j omega to be s here. Okay. So here, as I mentioned before, s is equal to sigma plus j omega. And if we put sigma to 0, then it becomes Fourier transform. So we can see that Fourier transform is a subset of Laplace transform, and Laplace transform is more popular in the system analysis or in our perspective, engineering signal processing. Okay. Now let's look at the discrete Fourier transform. Consider that we don't have infinite numbers of coefficients for this transformation. We only have limited number of samples in the discrete signal. Okay, and they are separated by t. And then the original Fourier transform can be converted to a discrete summation of the samples, which is equal to the summation of xk, x of k times e to the minus j omega kt. Is a summation from k equal to 0 to k is equal to n minus 1. Okay, and t here is the sample time. Okay. It's also based on the assumption that the signal is periodic with the fundamental frequency omega 0 is equal to 2 pi divided by nt. Okay. Again, here I shows the pair of the formula for the discrete Fourier transform in terms of the xn, which is actually projected from the time domain to frequency domain, and that the sk here is actually is also called inverse discrete Fourier transform. Okay. For the detailed derivation, I also provide link here. Okay. The other similar transform, which also apply in the discrete signals, is also called Z transform. It's actually corresponding to the Laplace transform, which is applied in the continuous signals. Okay, and this transform is actually project the signal into Z plane. Okay, if we look at Z variable here, is actually equal to R times e to the st, and if consider unicircle, which is R equal to 1, then the Z transform will be downgraded to dtft. Okay. All right. So the reason why we mentioned about Z transform here, because Z transform is very popular, very useful for our filter design, especially for the digital filter design. Okay. All right. So I believe we already learned more. There's something about their processing errors like aliasing and leakage. Okay. Now let's revisit these two errors in the context of the discrete signal processing. Okay. So imagine that we have the n separate samples have with the sample time t. Okay. If the t samples, number of samples are not sufficiently closely spaced, then it cannot fully represent the original signal. Okay. And that will cause aliasing. So the figure bottom here shows how the aliasing look like, right? So the high frequency component and low frequency component, they are mirrored and they are kind of share the same frequency magnitude after the sampling. And in that case, we cannot fully represent the original signal. Okay. The solution is to increase the sampling rates, or most effectively, to use anti-aliasing filter to filter out the high frequency components before we do signal processing. Okay. The other issue is the leakage. So, as I mentioned before, the discrete time signal processing assumes that the signal can be represented using an integer number of cycles. Okay. But if the original signal is not able to, to realize by it can only be realized by non-integer number of cycles, then we will have some kind of discontinuity. As you can see here, this sharp change of this time history signal will actually related to the leakage issue here. Okay, and the solution is to use the window function, which try to reduce the edge value, the value in the edge, try to be minimize that value close to 0 is such that the reconstruct signal will not have this kind of discontinuity, and we can mitigate the leakage issue here. All right, so in this slide, I try to put all of the common transform techniques together in the same table, and try to kind of clarify their assumptions. So hopefully you can get better understand about which transform or which technique you need to use for your purpose. Okay. So we have Fourier transform, Fourier series, Fourier transform, discrete time Fourier transform, discrete Fourier transform, Laplace transform, and Z transform. And they actually or project the signal from time domain to frequency domain. But Laplace transform is special, is projected to S domain, and Z transform is for the Z domain. Okay. And as I mentioned before, if we consider the sigma, which is magnitude, to be 0 for the S variable, then the Laplace domain, the S domain will be a kind of downgrade to the frequency domain. Okay. Similar for the Z transform. Okay. And this just shows how what is the relation between these several transforms in their specific domain. Okay. The other thing I would like to clarify is that the signal processing, they have their special assumptions. Okay. For Fourier series, if we transform signal from time domain to frequency domain, we're assuming that the signal in time domain is continuous and is periodic. So if we check their formula, it's actually their summation from minus infinite to infinity. Okay. But for frequency, from frequency domain transform to the time domain, then it seems that the signal is discrete, okay, and it is aperiodic. Okay. But for Fourier transform, it's different, okay, and it actually deals with the signal that's the fundamental frequency is almost close to 0, such that it can represent aperiodic signals. Okay. And for frequency domain transform to time domain, then it becomes continuous because of that. Okay. Similarly, it also shows there's some assumptions for the other transform techniques. I will not go through all of them. But we can discuss more afterwards. All right, so now hopefully you already have a better idea about what kind of signal processing technique that we can use for our digital signal processing. Okay, different transform actually. And now let's think about how do we design filter. Okay, as I mentioned before, filters are the major components for the digital signal processing. Okay, the filter is actually could be a device or a process. The device could be an analog filter that built upon the different circuits, and the process here represents their data analysis, but it's in program. It is programmed in the chip or in the microprocessor or computers. And the filter's purpose is to remove the unwanted features from the signal. Okay. Depending on its output, its performance, it can be classified as the high-pass filter, low-pass filter, high-pass filter, band-pass filter, and notch filter. So here we show the kind of illustration here. Assuming that we have original signal, it has complex signal, consists of different frequency components. Okay, from low frequency component to high frequency components. So the low-pass filter is actually filter out. Remove the high frequency components, but only lets the low frequency component be remained. Okay, and the high pass filter is operating in the opposite way. So it passed the high frequency components, but blocked low frequency components. So the band pass filter is that it lets the frequency the signal of the certain frequency band to pass through, but it remove the rest of the frequency components. Okay, and a notch filter is opposite in the it is operated in the opposite way. Okay. All right. So filter actually can be classified into two types. Okay, analog filter and digital filter. Okay, analog filter is actually built upon their hardware circuits. It usually consists of, made of the resistors, capacitors, etc. Okay, and it deals with the analog signals. And digital filter is different, so it actually deals with the process the digitize the signals, and it is actually sitting in the microprocessor or computer chips. We can program it in the software. Okay. And they have different pros and cons. Okay, analog filter is actually easy to assemble. You just put different circuit together, but it's less accurate. You cannot control the behavior of that as the user expected easily. Okay, and the digital filter is actually easily to adjustable. Right, you can just change some parameters, and also is usually usually accurate to achieve the performance that user expected. Okay. But can we replace all the analog filter? Absolutely no. So one example is that to address the aliasing issue, we need to apply anti-aliasing filter, which is actually put before ADC, before the signal is transformed from analog to digital. Okay, and that's for that part we need anti-aliasing analog filter for that purpose. Okay, and digital filter is easier to program, is more powerful for applications, but we need to think about the trade-off between accuracy and computation costs, especially for the real-time data processing implementation, right? So if they're usually more accurate, performance require more complex behavior, and that require more memory, more time to compute. And in that case, there's a concern about, can we realize all the analysis within one step, such that the entire process can be implemented in real-time analysis. Okay. All right. So today at this lecture, we were just focused on digital filter design. Before we go to the details, let's just go through some basic concepts for digital filter design. Okay. So the figure right here shows the filter in the frequency domain. Okay, the black curve, the square, the step signal here represent the idealized low-pass filter. Okay, however, we can never realize this ideal low-pass filter. Instead, we can just kind of to approximate this behavior, right? So the blue curve is a typical filter response in the frequency domain. Okay, so regarding that, we can see that we can kind of divide the frequency domain for the filter to be pass band, which is in this location, and also the stop band, which is actually within related to the frequency band that is blocked. Okay, and they will have some ripples here. Okay, for some filters we can mitigate that, but it's not easy to completely remove that. Okay, and between them, this is the transition band, because we can never realize this idealized brick wall filter. Okay, there's always kind of small transition here. So the associated property is, how do we determine the cutoff frequency, right? For the brick wall filter, this line is actually corresponding to color frequency. But for the practical perspective, the color frequency is actually determined by 3 dB roll-off, which is actually check the magnitude. If it is if the magnitude is kind of 1 minus 3 dB, okay, 1 dB minus 1 minus 3 dB here, then that represents that means that the power of the signal is reduced by half. Okay, and that corresponding frequency is called color frequency. Okay, and we also need to pay attention to the filter coefficients. In the convolutional representation, filter can be represented as a series of the coefficients, and the number of coefficients is actually represent the length of filter. Okay, and the filter order is actually, you can think about the transfer function of filter, and then pick up the highest exponent represent the filter order. In general, the filter order is equal to the filter length minus 1. Okay, and usually digital filter will always have the delay here, and the group delay is equal to n minus 1 divided by 2. Okay. Now let's start with some very basic filter design. Let's use the Z transform first. Okay, imagine that, and I think the most easier understandable filter is the moving average filter. So imagine that we have this stock price oscillate very a lot over last 100 days. This is actually Alphabet company stock price. Okay, and so the question is, can we get the average stock price every 10 days? Okay, then the solution is to apply the moving average filter. So so if you think about convolution in time domain, it's actually very easy. It's actually the yn, the result, is actually equal to the average of the summation of previous 10 days. Okay, so n here is actually 10 for this problem. Okay, and then we can apply Z transform. Eventually we can obtain y of z is equal to n divided by n, 1 divided by n times the summation of x of z times z to the minus k here. Okay. Similarly, we can similar to frequency response, we can apply the we can obtain the transfer function h of z here. Okay, and then we can replace the z with e to the st or e to the I omega t. Eventually, we can obtain the frequency response. Okay. So this is the frequency response for the n-point moving average filter. Okay, and I already calculated that. So here is the result for the 10-point moving average filter result. So this is this. In other words, smooth stock price curve. Okay. And if we add more points, I mean increase the n, you have even smoother line there. Okay. So here it shows the frequency response for the moving average filter. So the blue curve is the represent to the 5-point moving average filter, and the yellow curve is the 20 points. So as you can see here, adding more points, it actually has filter out more wider high frequency components. Okay. Also, the moving average filter is essentially a low pass filter, but it's not quite good or quite high quality a low pass filter. As you can see here, it has very large ripples in the stop band, and also it has very large long transition band here. Okay. But anyway, this is a very easy, understandable filter. We can actually implement the n-point moving average filter in another way. Okay. If you compare y of 20 with y of 21 here, you can see that they have almost 19, they have 19 data points are identical. Okay, so eventually you can say that you can represent in a recursive form. Y of n is equal to y of n minus 1 plus 1 over 10 times xn minus x of n minus n. Oh, there. So actually the result is the same, but it's very fast. It doesn't, it's not, it is very fast for implementation. It doesn't need to deal with calculate the 20 previous inputs again, but it just need to kind of use the previous output, but it just updates one input. Okay, it's easier, it's faster to implementation, but it depends on the previous output. Okay. Again, we can repeat the previous process by applying Z transform and then obtain the transform frequency response function here, which is h of the omega. And then if we do some additional derivation, you can eventually find that this is actually equal to the transfer frequency response function that we obtained before. Okay. So here, for summary, okay, purpose, using Z transform to design filter. First of all, we represent the filter in the difference equation. Y of n is equal to a summation of the previous input minus the summation of the previous output. Okay. And then we apply the Z transform to, change from time domain to Z domain. Okay. And then we obtain the transfer function of the Z domain, and then replace the Z with E of J omega. Okay. And then eventually we can obtain the transfer function in the frequent domain. Okay. All right, so now let's think about more generalized filter design. We will use windowing function. So first of all, I would like to introduce one common type of the digital filter, which is also called FIR filter, finite impulse response. Based on that terminology, we can understand that this impulse response has limited number of non-zero values. Okay, which means that if we consider the filter in the convolutional representation, which is actually equal to convolution of the impulse response with the original signal, is actually equal to sorry, is actually equal to the summation of the limit number of the convolution of the filter coefficients with their original signal. Okay. So the general process for the FIR filter here design is that we first clarify our requirements, which is what kind of frequency response we want to obtain. Okay, and then we do inverse Fourier transform to get this impulse response. But that's actually has infinite impulse. So we truncate the impulse response by using window function. And then we shift that impulse response. Eventually, we obtain the finite FIR filter. Okay. Let's go through a simple low-pass filter example to better understand that. Imagine we want to have a low-pass FIR filter with a color frequency for 2 Hz for the for the original signal with the sampling rate of 10 Hz. Okay. So this is the frequency response. Okay, we have the band of between minus FC to FC, and the magnitude here is 1. Okay, so this is idealized low-pass filter. We first apply the inverse Fourier transform. We obtain the GT by using the inverse Fourier transform formula. We can obtain that GT is actually equal to 2 times FC times sinc of
to FCT. Okay, so this sinc is actually represent the sinc function. We already showed that before. That is corresponding to the square signal. I mean the frequency.
Fully transformed pair. Okay, and it's actually equal to sine x divided by x. Okay, this is a continuous form of GT, and for filter design, we use the discrete form, which is discrete samples of GK here. Okay. All right. So by applying the inverse Fourier transform, the frequency response
can obtain the kind of the sinc function here. Okay. And the blue curve is the GT, the continuous form, and GK is the sample form. Okay. But this is actually infinite, so it's extend to the left to the minus infinite, and then extend to the right to the infinite. Okay, infinity. Okay. This is actually not easy to implement because we need infinite number of coefficients to do the convolution of the original signal to obtain our expected signal. It's not easy to do, and so to get around this problem, we truncate the signal. Okay, we assume that beyond maybe 10 points, I mean from the center here beyond 10 points, we assume that the other data points we can neglect them, assume that they are 0. Okay, and then we shift that to the right by 10 points. Okay, so this is the shifted, truncated and shifted impulse response. Okay, so in here we have total number of 21 data points. Okay, and this is the kind of the representation for the truncated impulse response here. And to examine its performance, here's the results in the frequency domain. Okay, again we have idealized low pass filter, which is the brick wall filter here, which have very steeper transition here. And for the truncated low pass FRA filter, the black curve here shows the order of 10. Okay, which means that we truncate the number by 5 and then move another 5 here. And the argue curve actually represents corresponding to the left impulse response here. Okay, as you can see here, if we truncate more coefficients, the resulted transfer function is closer to the idealized low pass filter. Okay. The other issue we need to pay attention to is that in the frequency domain, there always have a kind of ripple here. This is because we have abrupt ends because the truncating. Okay, and to mitigate that issue, we can apply the window function. Here we already apply the window function, which is actually the boxcar window. We don't do any weighting. The weight for the boxcar window is always 1. So from the first point to the last 20 points here is only multiplied by 1. Okay, and we can apply more advanced window to get around that issue. Okay, and it actually can represent as the weight omega times the impulse response. GK. Okay, and this is for common window function. Okay, including Hamming window and Henning window. So here's the results. If we apply Hamming window or Henning window, we can mitigate or get rid of, or almost get rid of the pulse, the ripple in the stop band, in the pulse band here. Okay. All right. So hopefully you get a better understanding about how to design an FIR filter, low pass filter. Okay. using the window function. Now let's think about another common type of the filter, which is IR filter, infinite impulse response. By definition, the impulse response is infinite, okay? And most recursive filters are IR filters. So here, IR filter, they not only depends on the previous current and previous input, but also depends on the previous output, y here, okay? So the way to design IR filter is that we first obtain the transfer function that we expect to kind of manipulate the original signal, okay, with poles and zeros, etc. And then we do the transformation to Z-plane using bilinear transformation. And then we change the equation from Z-plane function to the difference function, and then we can kind of rewrite that into kind of convolutional representation of the IR filter. So most IR filter they actually have their analog filter equivalents. Okay, so in other words, we don't need to worry about the transfer function build up. I mean, how to realize the transfer function. We just follow the well-standardized, well-established transfer function for the corresponding analog filters. Okay, or you can also, starting from scratch, you can design poles, determine poles and zeros, and build your own transfer function, and then you transform to Z-plane, and then you further apply the difference function here. Okay. The figure here shows several common types of the analog filters, including Butterworth filter. So it actually doesn't have a ripple in the passband and stopband. Okay. And check-shape filter type 1 and type 2, it actually has ripple in either passband or stopband. For type 1, the ripple exists in the passband, and for type 2, the ripple is located in the stopbands. And then another popular analog filter is elliptic filter. So it has most steeper transition than other filter of the same order, but it has the symmetric ripple in both passband and stopband. Okay. Before we give an example about how to design our filter, maybe we need to spend some time to clarify what is the bilinear transform. It actually is transformation from S domain to Z domain. Okay. So remember, Z is actually equal to E of ST. Okay. And by some derivation, and then approximately we just pick up the first item of the expansion, then we can obtain that S is actually approximately equal to 2 divided by T times 1 minus Z of minus 1 divided by 1 plus Z of minus 1. Okay. To visualize the relation between these two domains, you can see that the points in the imaginary axis is actually projected to the points in the unit circle, which is curve B here. Okay. So any points in the left part of the imaginary axis is actually located to the points within the unit circle. And the points in the right hand of the S plane is actually corresponding to the points outside the unit circle. So if we want to design filter or transfer function, if we want a stable pole in the left zone of S plane, is actually corresponding to the points inside the unit circle in the Z plane. Okay. So one thing we need to pay attention to is that this is approximate linear transformation, approximation, right? And if we have relatively large value of the S or omega, then they are not mapping together. Okay, in a linear way. Okay, so imagine we have analog frequency. Corresponding value of S here is actually equal to J times omega A, and then we apply the formula here by several steps of derivation. We can find that is actually equal to 2. It is actually corresponding to the nonlinear projection to the omega d here. So omega d is actually corresponding to the digital frequency. So analog frequency omega a is not a linear function of omega d here. If we visualize their relationship, here shows how it looks like. Okay, so if the omega a or omega d is smaller, then we can assume that they are identical. But if we have relatively large omega a or omega d, then they are not mapping, not identical anymore. Okay, so in other words, we need to pre-warp the frequency for some points, like for color frequency, attenuation frequency, etc., before we design a filter. Okay. All right. So now let's go through a simple example to better understand that. Okay. Let's design a digital low-pass Butterworth filter. Okay. So this is how the Butterworth filter look like. We want color frequency to be 2 kilohertz, and the sampling frequency is 10 kilohertz, and we want it there. The stop band, has the minimal attenuation of 30 dB at 4.25 kilohertz. Step number 1, as I mentioned before, we need to pre-warp the frequency values. Okay, let's start with the color frequency here. By applying the formula, we can transform the obtain the corresponding analog filter omega A1 of the omega D1 here. So the result is 14.53 times 10 to the 3, okay, radius per second. Okay. Similarly, we can obtain the pre-warped analog frequency W omega A2 here. And then the next step is to determine the order of the filter. So the Butterworth filter is easier to design because the main parameter to determine the filter is the order n here. Okay. It actually has a well-established formula for the transfer function and also the attenuation formula here. So it actually is equal to, A here is the magnitude attenuation. Is actually a function of the order n here. So by applying the condition that we want 30 dB is actually corresponding to 10 times square root of 10 in the amplitude reduction, and then we apply the corresponding pre-warped analog frequency omega A2 and omega A1 for the color frequency. Eventually, we can obtain that the minimum order of the Butterworth filter is 2. Okay. Therefore, we can just utilize the well-established second-order Butterworth polynomials for this transfer function. Okay. By applying the Z transform, we can, by substitute S with the formula of 2 divided by T times 1 minus Z of minus 1 divided by 1 plus Z of minus 1. Okay. And then by substituting the color frequency WC here, omega C here, we can eventually obtain the transfer function of the Butterworth, the second order Butterworth polynomial equation here. Okay. And then we can expand that. Eventually, we can obtain the difference equation, which is actually the current output is equal to the summation of the current input with some weight here and the previous two inputs, and also previous two outputs. Okay, this is definitely a recursive filter, and also is an IR filter. Okay. All right, so we already go through the basic concepts of FIR and IR filter, and also go through a simple example. Okay. Now let's compare them together. Okay. As I mentioned before, FIR filter, the current output is only depending on the current input or the previous input. But the IR filter is different. That is also depending on the previous output, which make it as recursive filter. Okay. How does their performance look like? Okay. So here is a comparison between the 14th order FIR filter with 4th order Chebyshev filter. Okay. They have comparable performance, but as you can see here, the IR filter doesn't have the linear phase, so it's nonlinear for the pass band. Okay. But the good thing is that to obtain the comparable performance, the IR filter only need 4th order, but the FIR filter need 14th order. The order is much higher in FIR compared to IR filter. Okay. In more details, I put everything into the table for your information. Okay. As I mentioned before, FIR filter, to obtain expected performance, you need higher order, but it has a linear phase. Instead, IR filter is hard to control its phase. Okay. FIR filter is always stable, but IR filter has the potential of this instability because it also depending on the previous input, the previous output actually. FIR filter is easy to design because you just need to kind of figure out the frequency response and then do some additional analysis. But IR filter, they usually follow some analog equivalent filters, and also you need to think about more detailed design considerations to tune the parameters for IR filter. Okay. So it's not easy to design. Although the example that we've shown before is not difficult. Okay. For the implementation, because FIR filter needs higher order, which means that it need more coefficients and need more memory to store, and also eventually need more time, computational time to implement. Okay. And because of its high order, it usually has high latency there. Okay. But IR filter is different. It's easier to implement. It has low latency. So in summary, it depends on the requirements of the implementation and design. So depending on that, you can choose which one is better, okay, for your application. All right, so now let's think about, okay, so I think we already go through the basic knowledge of signal processing. We go through how to design a digital filter. And now let's think about some interesting applications. If we have this digital filter technique, how do we apply them in the real engineering problems? Okay. The first application I would like to go through is the online downsampling. Okay. So this is actually related to my PhD project. So we have the wireless smart sensor X node, and it has baseline sampling rates 1 kilohertz, and but the different application require different sampling rate, right? 500 hertz or even 10 hertz. Okay, but how do we kind of obtain the low rate samples from the baseline sampling rate measurement? Okay. So that's a problem. Okay, as I mentioned before, for the real implementation, real world implementation, we need to consider about how much time each step filter will consume and how much memory it will consume. Okay. We need to make sure that it's effective and efficient. Okay.
It's also similar for the DAQ system, right? So if you select the sampling rate, it also do kind of online downsampling based on their baseline sampling measurements. Okay, so this is the one of the table that I found one of the papers for the XNO development. Okay, so the left column shows the decimation rates, and also here shows the detail about the auto filter. As you can see here, the more decimate rates we have, we need a more higher order filter. Okay, and the calculation time also increase. Okay, the good thing is that all of them are below 1 millisecond, which is the limited time interval for real-time implementation. Okay, corresponding to 1 kilohertz. Okay, so the interesting thing that if we go to 100 decimation rates, the filter order will be extremely large, could be 1,000 order. Okay, so the way to implement that is instead of using single filter, we implement two consecutive filters, which means that the data samples from the initial baseline measurements, it goes to the first filter, sample at maybe 250 hertz, and then go to next digital filter to sample to be 20 hertz. Okay, so the filter here is actually low pass filter because if you just want to downsample, you need to get rid of the high frequency components. Otherwise, we will have some aliasing in your signal. Okay. The second application, interesting application, is about interstructural drift estimation. And it is actually essentially a high pass filter. So interstructural drift is a very important indicator for us to estimate the buildings under earthquakes. Okay, but the direct measurement is very expensive, right? You need, for example, LVDT. You need to fix the ends, both ends of LVDT in the two consecutive floors. Okay. So then research think about, can we just use acceleration, right? And then we do double integration. We can obtain the displacement, and then we compare the displacement of the two floors. Then we obtain the interstructural drift, right? But the problem is that if you look in detail about integration, their initial noise after integration were amplified to a very crazy number. So this is how it shows. Look, this illustrates how it looks like, right? After integration, we will have crazy integrated results compared to the exact value. Okay. So the solution is to apply high pass filter to kind of filter out the low frequency noise. Okay. So in our paper, we use gravity acceleration, and then we define our filter, which can perform both double integration and high pass in the same time. Eventually, we can obtain the interstructural drift. Okay, so this is the illustration. I mean, compare with their result from their drift filter, interstructural drift estimator, with their exact ground truth value. Okay, and then we can use that as an indicator to kind of approximately estimate the building conditions. Okay, but the tricky part is that because in order to get rid of the noise, I mean low frequency noise, we completely remove the low frequency component. In that case, we can never obtain the residual displacement, which means that we can only obtain this relative displacement, right? Because we are kind of missing some initial low frequency components. So that's actually the main drawback for this solution. All right, so but we can still address that using advanced filters. Think about we have multi-source of data. We have acceleration, but for integration, the low frequency noise will be very harmful for the accuracy of after integration. So we need high pass filter to get rid of the low frequency noise. And then we have another source of measurement. We have vision-based display measurement, like camera. It is doing very good job for low pass for the low frequency measurement, but it doesn't do a good job for high frequency measurement for the camera. Okay, but can we just combine them together? Okay, think about that. So we can fuse the data from these two sources of measurements. This is how it looks like in the frequency domain. So the orange curve corresponding to the signal of their acceleration. Okay, and the blue curve is corresponding to the vision-based displacement. Okay. Can we just kind of take advantage of both measurements, and then we can eventually obtain not just the relative displacement, but also the absolute displacement. So that's the idea for this data fusion using filters. So this is how the filter looks like. This is called complementary filter. It has high pass filter, which is a red curve here, corresponding to the acceleration for acceleration integration, double integration. And then we have low pass filter, which is corresponding to vision-based measurements. By kind of combine them together, we obtain the overall representation of the measurement. So the figure here shows the arrow for proposed solution and vision-based solution. So the proposed solution doing a very good job. All right, so next step is to demonstrate how do we kind of design that in our purpose, right? Okay, good thing is that MATLAB already provide all of the essential formulas, equations for us to use. We don't need to dig in detail about how to do the Fourier transform, etc. And we can just easily apply the function, which is very good. So the remaining part of this lecture is to go through these functions and to do the demo such that you can better understand how to apply that, how to design the filter in your own applications. Okay. So for basically, we start with the Z transform design. For the filter design, we can use filter function. Okay. It needs input of B, which is the coefficients in the denominator, and input for A, which is corresponding to the information and the coefficients in the denominator. Okay, and eventually you can obtain the filter function. So in the demo session, we will practice how to design 10-point moving average filter. So for filter design using window function, MATLAB command fir1 and fir2 can realize that. Okay. So the difference between fir1 is fir2 is that fir1 can only consider basic filter like low pass, high pass, and band pass. Okay. But if you want to design a kind of piecewise linear frequency response, okay, you probably need fir2 that can help you to consider that. Okay. In the practice, we will go through how to use this function to design low pass and high pass and band pass filters. Okay. For the IR filter using specific functions, the MATLAB has the built-in analog filter equations, formulas, Butterworth, Chebyshev 1, Chebyshev 2, and elliptic filter. Okay. We will also go through the Butterworth and elliptic filters in our demo course. Okay, demo section. Also, we can also design a filter using the filter designer, a GUI as shown here. We can specify the type of filter, high pass, low pass, etc., and also the design method, also the determine the order of the filter, and specify the cutoff frequency, pass band,
and stop band. Okay. And the result can be exported to both the window, the script or the Simulink model. So I also provide link for the detailed instructions. Okay. And following that, we will go through Simulink model to kind of emulate the aliasing and anti-aliasing, quantization and leakage, etc. Okay. We will also apply the filter to process the real-world data, the field testing data. So this is the setup that's in my PhD study. So we put sensors beneath the bin of the railroad bridge, and we measure the vibrational bridge when train move across. Okay, so this is data we got from the wire sensor. Okay, it has high frequency component, high rate measurement. So, but how do we kind of obtain the low rate measurements for other purpose? Okay, so in that case, we need to design a low pass filter. Okay,
to block the high frequency components. In that case, we can obtain the expected result measurement data in low rates. So in summary, we have
already go through the backgrounds of the digital signal processing. We review some basic transformation techniques for signal processing. We also we also study how to design digital filter, including FR filter and IR filter. And also we discuss several interesting applications using filters. And eventually we quickly go through the demo, the implementation in MATLAB. So that's it. Thank you for listening, for your attention. After that, we will have a chance to go through together to practice how to design the filter in the MATLAB and apply that in the real world data. Thank you for your attention.